I've kept up our diagram from the previous problem. We were trying to find maxes and mins of this function, f of xy equals x cosine y, subject to the constraint that we had points on the unit circle. And we said the unit circle was just a level curve for this function g of xy, which was x squared plus y squared. The unit circle is, of course, the level curve where that's equal to 1. Okay, now what we determined by drawing this picture, this circle here, that was the level curve for g that is my constraint curve. And then I drew a contour plot for f. And of course, anytime a level curve for f intersected the unit circle, that told us what the z value of f was at that point on the unit circle. So here, this point 0, 1 would map to 0 because it was on the level curve for 0. And we saw with this particular example that every time we actually crossed a level curve for f, we were bigger than that value on one side and smaller than that value on the other side. Okay. Now you might ask, would it be possible for a different function f to say this is 0, to have my function value being positive over here and positive over here so that this was a min? When I cross a level curve for f, do I have to go from being smaller than that value to bigger than that value or vice versa? Could I be smaller than that value on both sides or bigger than on both sides? The answer is yes, but that can only occur if this would be a critical point for the function f anyway. And we're going to ensure, as we develop our technique for Lagrange multipliers, that if there happen to be any critical points for the function that lie on that constraint curve or surface, that we consider those points. Okay, so we want to find any points that aren't anyway, any additional points that aren't already critical points that happen to lie on our constraint, but where we would have a max or a min. And we determined that was at these places here where the level curve for f touched but did not cross the level curve for g. Okay. Now, what that means is that at this point here, which we said was the location of our min, and at this point here, which was the location of our max, f and g share a common tangent line. Sorry, the level curves for f and g share a common tangent line. This line would be tangent to this level curve for f and tangent to the level curve for g, which was my constraint curve. Same thing over here. This line is mutually tangent to those two level curves. So how can I take advantage of that? Well, I'm going to think in terms of gradient. Okay. Now, if the gradient of f is 0, we're at a critical point. That's a point I care about. If the gradient of g is 0, I'm not going to be very happy because that won't give me a direction. So we are going to require that the gradient of g is not the 0 vector on the constraint. I don't care if it's 0 anywhere else. The function g was x squared plus y squared. That's defined on the entire plane. I care about this level curve, the unit circle. I want to make sure that my gradient for that function, the constraint function, isn't 0 on the constraint. Okay. If that's the case, I know something about the gradient. The gradient is normal to the level curve. That would mean that it would have to be perpendicular to this tangent line. So if this tangent line is vertical, at this point the gradient of g would have to be horizontal. Well, the gradient of f, if it's not 0, it's also got to be horizontal because it's also got to be normal to this vertical line. So what we'll have is that either I'm at a critical point for f anyway, so that f is the gradient of f is the 0 vector, or the gradient of f and the gradient of g are parallel to each other. They don't necessarily have to point in exactly the same direction. One of them could point to the left and one of them could point to the right, but they will be parallel to each other. Okay, that's sort of suggested by this example. Okay, Now, I'm not proving that the method of Lagrange multipliers works, but I wanted to use this example to suggest to you why it works. And now I'm going to state the theorem. Okay. If f of p, now I'm going to state it generically, so p could be a point in 2 space or a point in 3 space. This applies equally well to functions of 2 or 3 variables, even more, but we won't go there. Okay. If f of p has a constrained max or min subject to the constraint, g of p equals k. Now, if this p is a point in 2 space, this point is a point in 2 space. If I'm working with a function of 2 variables, my constraint is a level curve for a different function of 2 variables. If I'm working with a function of 3 variables, my constraint would be a level surface for a function of 3 variables. Okay. So if there's a constrained max and min, now that's an if, they're not guaranteed to exist necessarily. If the extreme value theorem applies, then they are. If it doesn't, who knows? Okay. But if there's a constraint, and if the gradient of g is not equal to 0 on the constraint, and I'm just going to have to write curve or surface because I'm giving you the generic version. Of course, it would be the constraint curve if I'm working with functions of 2 variables, and the constraint surface if I'm working with functions of 3 variables. Then the max min occur at a point where the gradient of f is lambda times the gradient of g. That's a Greek letter lambda. It's just standing there for a real number. This says the gradient of f is a multiple of the gradient of g. Okay. So there are basically 2 possibilities. If lambda equals 0, we have a critical point for f. Okay. Because that would mean the gradient of f was 0 times the gradient of g, so the gradient of f would be 0. Notice that means it's crucial that the lambda be multiplied by the gradient of g, not by the gradient of f. Because if lambda were 0 and I were multiplying it by the gradient of f, that would make the gradient of g 0. We can't have that. But I want to make sure that it's possible that I consider any critical points that happen to be on the constraint. So this ensures that if there are any critical points of f that lie on the constraint, I will consider them. If lambda does not equal 0, the 2 gradients are parallel. And that's what we saw in this example, because the level curves shared a common tangent line that forced the gradients, if they're non-zero, to be parallel to each other. Okay, excellent. So, how does that actually help us in finding that? We're going to have to look at algebraically what that implies, and that's going to lead to a nice system of equations. So we'll do an example of that in the next video.